Now to recap, we are checking if some number n is prime by doing a trial division. Here is the square root of n, and here is 3. Starting at 3, and we were hopping along by 2, up until the square root of n, and at each point in the way checking if that number divides n. Now, so far, people have been trying to reduce the number of steps we take by perhaps starting later and taking larger steps. Now, I just want to pause here and let's think about what is the ideal case for a trial division algorithm. What is the best we could possibly do if we got very creative in our stepping? Well, remember, any number n has some prime factorization, right? And let's say the square root of n is here. We actually only need to step on prime numbers. That would be the best we could do, because we know if we step only on primes, we will eventually find a factor, a prime factor if it's a composite. The question now is, how efficient is this method? Because it seems like we have a perfect solution now if we wrote a new algorithm which first just called the sieve. Let's say the new algorithm is calculating if n is prime. It could call the sieve and generate a nice long list of primes for us. And then we would have our trial division, which would use this list of primes, so it could hop along and hit only primes up until the square root of n, wherever that is. So what's wrong with this? Well, we can visualize the time complexity, or the number of steps taken. And remember, I did so by, I coded up this algorithm and I put in a step counter inside each loop. So we have, let's just say step plus plus means step plus 1 here. And inside this other loop, there's also a step counter, step plus plus. So these are all constant operations, checking if and marking. So we just have a step counter inside each loop. And now here is a comparison. On the far left is our old trial division method. In the middle is our algorithm just calling the sieve to generate all primes up to n. And on the right is this proposal where we just call the sieve to generate primes up to the square root of n, and then call trial division just on those primes. And let's see what happens with small input. As we can see initially, the sieve takes many steps. So even the modified version on the right is actually slower than trial division, and as the input grows, the number of steps in the sieve grows even faster. So let's just forget the middle and compare trial division versus the sieve up to the square root of n plus trial division. And here we can see the old trial division method is much more efficient. The number of steps in our sieve to square root of n plus trial division is growing much faster. So it is actually not an improvement. And below is the program I used to do this comparison, and there is a recording explaining how I set it up. But now you may be wondering, well, what if we calculated the primes in advance? So the first step would be to, let's say, build an array of primes and store it on a hard drive. And then our algorithm would just do trial division, and it would know how to hop on primes only because it would be reading from this proposed prime list. And perhaps our prime list stores all primes up to 20 digits or even 100 digits. Why can't we do this? Well, the problem is limitations in memory when we enumerate lists of numbers, which we'll explore next. And just for example, let's say we were doing this by hand. We calculate 5 was prime. We write 5 on a piece of paper and we store it in a filing cabinet. Then we get 7. We store that in the filing cabinet. 9 or 11, into the filing cabinet. And then we have a filing cabinet full of prime numbers. This is our, think of it as a prime array. Now, how big would this filing cabinet be if, say, we wanted all primes up to 20 digits or all primes up to 100 digits long? Could we even store this array on a hard drive? And to understand why this actually isn't possible, we have to dive a little deeper into how large does this actually grow, this prime array, and what is the size limitation of modern day and even future computer hardware.